Hello, I am Raffaele Zullo, and I'm going to talk about our work overcoming the sorrows of the young UDP options. Basically, we're going to show some path reversal pathologies affecting the recently introduced UDP options, and we're going to show how our solution, the checksum compensation option, can help to neutralize the most widespread of the pathologies. We all know UDP is a very essential transport protocol. A recent extension known as UDP options add the support for transport options to UDP datagrams. Basically, a surplus area containing UDP options is added at the end of UDP payload, leveraging the redundancy between UDP length and IP payload length. With IP payload length, we mean the IP total length minus the IP header length for IPv4, or IPv6 length minus the length of extension header for IPv6. A type length value encoding is used, similarly to TCP options. We have to notice that this modification to a UDP datagram affected directly or indirectly several feeds. Obviously, the IP total length, the surplus area itself, but also the UDP length semantics changes because it doesn't match anymore the IP payload length. And furthermore, UDP checksum and IPv4 checksum can be affected by this change. There are already a number of UDP options defined in the draft. They can help to solve a real-life problem. I give you just one example. The use of a transport layer fragmentation can benefit the DNSSEC and its larger responses. However, when we introduce a new protocol or an extension to a protocol, we usually face ossification. So it's important to understand if UDP options can be safely deployed. To understand this, we have tested a number of core networks and edge networks and identified several pathologies. Some of them are related to the UDP checksum validation. We actually observed 4 different computation schemes. Another one is due to a consistency check between the UDP length and IP payload length. We also tested for other pathologies, but fortunately we haven't detected them. These pathologies can affect middle boxes, but also network interface controllers and thus NDOS. Why the checksum is problematic, and this is the way UDP checksum is computed. We can see that UDP length is considered 3 times in the header, in the pseudo header, and as the number of bytes on which the checksum is computed. UDP header contains, by definition, the correct UDP length value, but it's possible that implementations use IP payload length instead of UDP length in the pseudo header and/or as checksum coverage length. And this is actually what we have observed. We have observed 4 different checksum schemes. Basically, they produce the same value for UDP, but they produce 4 different values for a UDP packet with the options. Obviously, the first one generates the correct UDP checksum, so it's Banyan, but a middle box implementing one of the other 3 schemes will discard packets with the correct checksum. After a preliminary survey, we noticed that the second scheme, the one using IP payload length for both pseudo header and checksum coverage, is the most widespread. And actually, a first sign of this was already found in a bug detected and corrected in FreeBSD during UDP options implementation. So we take a closer look at the difference between the correct checksum scheme and the scheme based on the IP payload length. We can see the delta between the 2 computations. And what we asked ourselves was, can we manipulate the packet? Can we actually add something, some sort of magic value that makes the 2 schemes generate the same checksum? And our solution was the checksum compensation option. Basically, to achieve this, we need a 2-byte field that can be conveniently encapsulated into a regular UDP option. And the value contains the 2-byte checksum of the options area plus a 2-byte pseudo header containing the length of the options, with some minor complications to keep the 2-byte alignment. But the most important thing is that this value is computed only on the options area, and this value compensates the difference between the correct UDP checksum and the IP payload checksum. So if we include the CCO in the options area at any position in the options area, a middle box will generate the same, will calculate the same checksum regardless of which which of the two schemes it implements. So understand if our option can actually help UDP options, and more generally, if UDP options can be deployed, we developed a TraceMore derived for mobile TraceBox, and this can basically generate UDP options packet with the 4 different checksum we have described, and it can use real application payloads, so we can interact with the real UDP servers. We have released the code at this address, and we can see 2 examples of what we can do with TraceMore. The first is a trace route analysis of a mobile network. We can see that the UDP packet traversed the network. The UDP options packet, according to the original specification, is blocked. In this case, it's actually blocked by a NAT implementing the IP payload checksum scheme, while the UDP options packet with the CCO can traverse the network. We can also test a DNS server. In this case, we see that for this specific DNS server, we receive a response to the UDP packet and to the UDP options packet with the CCO, but we don't receive any response to the UDP options packet without the CCO. So we can infer that actually that packet has not reached the destination. And this is what we have done. We have tested the UDP servers using DNS queries or stand-bin requests. And based on the subset of replies received, we can infer which packets have actually reached the destination. To increase the number of paths tested, we also targeted HTTP servers. HTTP servers are not supposed to reply to UDP datagram, but some of them reply with ICMP port unreachable, and so we can leverage these messages to infer which packet have reached the destination. Obviously, there are some further considerations to be taken into account. For example, the ICMP rate limiting, but we're going to see that the results will be quite close across the different categories. So basically, we have obtained a list of stand servers, IPv4 stand servers from a preliminary IPv4 scan, and a list of IPv4 and IPv6 authoritative DNS and HTTP servers from Alexa Top 1 million. Our test suite includes 10 datagrams. Each datagram provides specific information about the path. We have 3 datagrams three regular UDP datagrams to characterize the path in absence of options, and 7 UDP datagrams to detect interference with the UDP options. So the overall traversal rate of these 10 packets can give us a rough idea of what is happening. We can clearly see that the traversal rate of the packet of the UDP options packet with the correct checksum in blue is lower than expected, and is lower than other UDP options packet. For example, the packet with the IP payload checksum in red, that is actually a packet with a checksum that is supposed to be wrong. However, we have to combine all the outcome of all the test packets for each path to characterize the path and generate the next plot in which we see the paths broken by their pathology or pathologies. We can see that the paths on which only the correct checksum works in light green are a very small portion of the paths, while the IP payload checksum pathology is widespread, and it can be present alone in red, but also in combination with the Bannon pathology in pink and yellow. Specifically, yellow paths are the paths on which both checksum are accepted, but every other non-zero checksum is discarded, and we're going to delve into this case later. We can also notice that the third and the fourth checksum pathology are quite rare, but also that there's 60%, 16% of the path in gray, in which no UDP options packet can traverse, and this is most likely due to a length consistency check. Now, if we group yellow, light green, and dark green together, we get all the paths on which UDP options can be deployed according to the original specifications, while in red and pink we have the paths on which UDP options can be deployed only with CCO. And so we can better understand the next plot, in which we can see CCO contribution in red. we can clearly see that CCO significantly increases UDP options traversal rate. And for the first two categories, IPv4 paths to Stone and DNS servers, we can also see that the increment due to CCO is even greater than the number of paths originally traversed by UDP options. We have done this analysis also on a per AS basis. We can see the percentage of paths traversed by UDP options without and with CCO. For each AS, we can identify 3 regions. First, ACES in which all paths can be traversed by UDP options, and the contribution by CCO in red is quite evident. Second, ACES in which a subset of the paths can be traversed by UDP options, and in the majority of ACES, of AESs in this region, CCO provides an increment. And the third, ACES in which no measured path can be traversed by UDP, and this is a kind of specification that cannot be mitigated by our option. We also compared the use of CCO with the use of zero checksum for IPv4 as an alternative, but also for some specific UDP options that by design cannot be covered by a checksum, like light. And zero checksum is supposed to be always better than CCO, but this doesn't actually happen, because we have detected some interferences specifically with the UDP zero checksum that is also visible on regular UDP datagrams, not only with UDP options. Genesis of UDP options pathology. The checksum pathologies basically come from the ambiguity in the role of the two lengths, while the length consistency check can be due to, for example, discarding malformed packets. We got some feedback from manufacturers. One manufacturer explained us that the fault error for their stateful firewall was to discard all packets with an incorrect checksum, and the reason was that before applying a rule involving transport layer integrity had to be verified. Another manufacturer instead confirmed that their middle boxes perform a number of consistency checks on datagrams, including one based on the match between IP and UDP length. A common case in our results was the one in which correct checksum and IPPLO checksum are both accepted, but every other non-zero checksum is discarded. This cannot be explained by two distinct devices, because each device would discard the checksum compliant to the other. And we have observed, it can be explained instead if the two validations happen in the same device but at different layers. We have observed this in the wild, but also on devices that we had, like Linux workstation, Android smartphones, and noticed that the IPPLO checksum was accepted only when checksum offloading was enabled. Taking a look at Linux kernel code, we realized that basically when a packet is validated by the NIC, it's directly accepted. While if it's not validated by the NIC, it's verified again using the kernel routine. So this explains the dual checksum validation. But this is not banned, because we cannot use checksum offloading for UDP options packet, both incoming and outgoing. But CCO can help also in this case, because as long as we include CCO in the options area, then we can rely again on checksum offloading. So basically what we have done is describe traversal pathologies affecting UDP options. We have also shown how our checksum compensation option can significantly increase UDP options traversal rate. So what we suggest is to redesign the original option checksum to achieve CCO function, and we have to say that this has actually been partially done, and will be probably completed in the next revisions of the UDP options draft. Thank you for your attention.